So scientific notation is really used for one reason and one reason only. It's used to communicate really, really large numbers or really, really small numbers in a more eye-pleasing way. What do I mean by that? Right? So the mass of one gold atom. So if I took one gold atom in 8th grade, you all learned how incredibly tiny atoms are. We're going to learn even more how small they are here. If I took one atom and put it into a unit that I'm more familiar with, the gram, which is about one paperclip. One medium to small paperclip is 1 gram. Very, very light, right? You probably don't even know it's in your hand if you hold it there long enough. Okay? Look how incredibly, incredibly small that number is. Right here's your decimal spot. Right? That, you don't even know how to say that. I don't know how to say. I don't know what place value that is right off the bat. Right? It's incredibly small. Okay, so let's put it into the next unit. Like let's get 1 gram of gold. Right? But then I want to report how many atoms does it make to get 1 gram of gold. Well, then that number becomes incredibly, incredibly large. And I don't even know how to say that number. Right? It's even to the left of the decimal, right? It's more than 1. So how do I report that number? This does not look good on scientific findings, right? And so this is really small, this is really large, this is where we use scientific notation, right? So here's the basics of how to write scientific notation. In scientific notation, a number is written as the product of 2 numbers, all right? So the product of those numbers is, the basic format is, we have a coefficient, or I call your base number, and then that base number is multiplied, and I'm going to put a multiplication sign right there, to a power of 10. So the format is some number multiplied, by 10 with some exponent on that 10. That's your basic format for all scientific notation. And then there's some details to come along with that. Now, that exponent can be positive or negative. That exponent can be positive or negative depending on if it's a whole number or a number less than 1. The coefficient number is always positive. You'll never have a negative coefficient times 10 to the power of something. It's always going to be positive. And that coefficient number should always be greater than 1, but let's do this, but less than 9. Greater than 1, but let's do not 9, let's do 10. But less than, so 9.99999, that's okay. It's got to be less than 10. Greater than 1, less than 10. And this is the basics before we get into some examples. And if it doesn't make sense yet, once we do those examples, hopefully it does, okay? The last thing is, and we talked about this with some of the homework last class, where do I find my sig fig count? So if I look at a scientific notation term, where do I find my sig fig count? On the coefficient or on the exponent or them combined? What's that? On your coefficient. So on my coefficient, I also get my significant figure count. So how does all this happen? Where do all these numbers come from? Let's do an example. One of the most used scientific notation terms that we will use all year long is 6.02 times 10 to the 23rd. That is Avogadro's number that you see up here on this poster. All right, that's why I'm going to use it quite often to do examples. So up here, which one of these numbers is my coefficient? What is it? 6.02. Is it positive? Yes. Will I ever see a negative out here? No, I will not. What is my 10 raised to the 23rd power? Is that positive or negative? At this point, it's positive. Could it possibly be negative? Yes, it could, but it's not in this situation. Right? So we say 6.02 times 10 to the 23rd. Is my coefficient greater than 1 but less than 9? Yes, it is. What would be a bad example of this rule if I had 60.2 times 10 to the 23rd? Is this correct? Because it's greater than 9. So I need to move my decimal one more spot to get that 6.02. Is it, what's wrong with 0.602? What's wrong with that? That's less than 1. So that's not a good answer either. These are just little things that you can be self-checking when you do your homework. Okay? And the last thing is, in Avogadro's number, how many sig figs are there in my term here? 3. Where do I get that? From my coefficient number, 6 and 2 with a sandwich is 0. See all that information we can get from there? All right, that's how you write scientific notation. So you're going from standard notation into scientific notation because the standard notation is too incredibly large. All right, well, that's the reason. Now we'll do some work with a lot smaller numbers just to practice with the skill. Okay, so the number 4,500. The number 4,500 is written in scientific notation as. So here we go. What do I need to do? Well, if I kind of blow this number up a little bit, where is my current invisible decimal spot? Behind the zeros. Would you all agree with that? Yes? Is the number currently between 1 and 9? It's not. And I need to write this in scientific notation, right? Which means I need something to the power of 10. How do I know if my exponent is going to be positive or negative? Well, is this number greater than 1? If it's greater than 1, it's going to be positive. If it's less than 1, it's going to be negative. But right now it's greater than 1, so I know I'm going to have a positive exponent. Right? Well, how do I know what that exponent's going to be? Well, let's get this number between 1 and 9. So that means I need to move this decimal until I reach that goal of between 1 and 9. So right now I have 4.5. Is that between 1 and 9? Yes? There's my coefficient. How many times did I move the decimal to get that coefficient correct? How many jumps did I make? 1, 2, 3. What's significant about that 3? That becomes my exponent. And again, how do I know that's a positive exponent? My number is over 1. My number is over 1. So if I get rid of that, here's all of those things that we just talked about. Just in a slightly, let me go back, in a slightly different way. Any questions with that? Okay, so if I look at this, 65,000 kilograms, show me the work on how they got to with the jumps and moving the decimal, all that kind of stuff. Like, how would you do that if I didn't show you, go back, that answer? Like if you didn't know that. So you need to put 65,000 kilograms into scientific notation. How would you do that? Go and try to write that out without looking at the answer. Show me a little bit of work. Show me your jumps. Show me you moving the decimal, stuff like that. Is it a positive? Is it a negative exponent? And you think to yourself, why? Because there will be essay type questions on your test. I could very easily give you this question and I'll say, why? Like, why would I want you to put this in scientific notation? Why do we put anything in scientific notation? Anybody remember like the first thing we started the lesson out as? Just to make it more eye-pleasing for big numbers or extremely small numbers. To make it easier to communicate the findings or the term. All right? So we move the decimal until there's one digit to the left. And then there's the positive and negative explanation. If you don't already have, most of you probably already have that down. Or something along the, don't rewrite just to act like you're being busy. Okay? A lot of what we do in here is examples. That's important. Okay? Only include sig figs. That's the last thing. Right? So if I give the example of let's go back. Right? You can't see that. If I said 6.02 times 10 to the 23rd, how many sig figs are in that term? 3, right? And if I said, write this scientific notation into standard notation, first off, it'll take you a little bit to write all those zeros. But how many sig figs should you report in your standard notation? 3, because that's what's in the question, right? So just be aware of that. That's going to come up a couple times in the future. All right, we talked about that. We'll work on those. All right, so when we go from scientific notation into standard, so we're just undoing what we just did. So now I give you scientific notation. Jonah, why don't you move right here, man? Now we're going from scientific notation. Now we want to write it in standard form. Okay? And so now we're undoing what we just did. So now we're moving the decimal back to where it was. So here we go. So if I asked you to write this into into scientific notation, let's come down to this one. Here we go. Number 9. So I give you scientific notation. You need to give me what it would look like if I wrote it all the way out. So where is my decimal right now, the invisible decimal? Right after the 7. And now that negative means, will I have a number greater or less than 1? Less than 1, right? So which way should I move the decimal? To the left or to the right to get an answer less than 1? To the left. How many times should I move it? Right there. That tells me how many times I should move it to the left because it's negative that many times. Now, a common mistake that I see is they're like, okay, that's a 5.12345.7. Is that correct? No, what they didn't account for is that first jump to get the decimal to the left of the 7 first, right? So how many zeros should I have? 4, then the 7 kilometers. Okay? And there it is. Right? Try the next one on your own. 6.2 times 10 to the 4th millimeters. You need to get that into standard notation. All right, here we go. Camilla, will I have a, which way am I moving the decimal, to the left or to the right? To the right. Why, Jonah? Because it's a positive exponent, right? So that means I'm moving it to the right. How many times am I moving it to the right? Jacob?
The number of the exponent.
Which is what?
4.
4. That's how many times I'm moving it. So 1, 2, 3, 4. Every time I see a jump, I'm adding a 0. So if I rewrite that, 6.2, 1, 2, 3, 4. There's my new decimal. Fill in zeros. So my new number is, there you go, 62,000 millimeters. Here we go. This is somewhat of a challenging one, even though it seems incredibly easy, right? Write this in scientific notation, just the number 8. By all means, talk about it if you need to. Look at somebody else's and talk to them why they wrote what they wrote. This class is very much discussion needed to do well. Three, two, one. Eyes on me. So I want scientific notation, right? So in scientific notation, I have to have a coefficient, and that has to be multiplied to a power of 10, right? It has to, because that's scientific notation. Yes? So we start with 8. Is that between 1 and 9? So we're already good there. How many times did I move the decimal to get to 8? Oh, I'm sorry. I keep forgetting that thing there. So if I go 8 times 10, how many times did I move the decimal? There you go. If you don't believe me that that's a real thing, go to your calculator, go 8 times 10, caret button, 0, see what pops out. If you don't, believe me, if you just want to check it out, it should be 8. Okay? So that is okay. So what you need to do right now is, when I'm multiplying or dividing using scientific notation. So an example would be 2.1 times 10 to the 5th divided by, let's say, 0.25 times 10 to the 3rd. Now, if you're going to put these terms into your calculator, you can. This is a long way to do it, but make sure you put parentheses around these for order of operations. That's incredibly important. Does anybody know the fast way? What happens, what function can we do when we divide by exponents? We subtract, right? Because these are all base 10 here. We can just take 5 minus 3. That's my new exponent. Yes? What about my coefficient? Go to your calculator. What's 2.1 divided by 0.25? What is it? 8.4. There's my answer. Or you can plug all that into your calculator and push enter and it'll pop out the right answer. Okay? If you would multiply, let's say we go 2.1 times 10 to the 3rd times 0.2, let's do 1.2 times 10 to the 3rd. What do I do with my exponents now? You add them up. You add them. So now it's 10 to the 6th. 2.1 times 1.2 is what? 2.2? Anybody? whatever that is, times 10 to the 6th. Okay? So that's how you multiply and divide, use in science. The US or the metric. So you already know the metric system, right? And the metric system is actually very, very easy to use if you grew up on it. Like, Spanish is what I've heard a lot easier to learn initially than English. English is a hard language, okay? But because most of us have learned English since we're a baby, and not Spanish, that's why it's difficult. If we would have learned metric from the beginning, it'd be incredibly easy to use, which is why 95% of the world uses it, except for us. Okay, there's about 2 other countries that don't. But the international system is also for the metric. So what you're going to need to know is this table right here. And most of you know this stuff, but if you don't, you need to write it down. These are base units of the metric system. These are base units of the metric system. That base unit is going to be incredibly important when we go to convert from one unit to the next unit. Okay? So time is seconds. That's universal. Length, mass, temperature, and volume is not on here, and it should be. Let me make sure my pen is ready. There we go. Volume is the liter. That's a terrible R. Liter. Now, this temperature is really the one that you may not have heard of, and the amount of a substance is the mole. We will talk a lot about the mole, about the second semester all the way through. And the temperature in Kelvin. Does anybody heard of the Kelvin scale? Does anybody know what that scale is called? Absolute zero, the absolute scale. Okay? Absolute zero is when matter ceases to move, which the movement of the particle causes temperature. And so you can't get slower than stopped. So if matter has stopped, that's what we measure as absolute zero. Okay, and that's on the Kelvin scale. And then the Celsius and Fahrenheit have been degreed off of that Kelvin scale. So we use the Kelvin almost exclusively in this class, and we'll have to convert into the Celsius sometimes as well. Or out of Celsius and into Kelvin. All right, everybody good with that table? These are your base units. That's going to be very important when we go to convert, knowing what these base units are. Now, this mass gets a little bit funky because it's technically kilogram, but for the base unit, we're going to use the gram. And it's just one of those things, one of those details. Okay, so length is the meter. I'm not going to spend a lot of time on that. If I look at, here's a little skill. If I look at that measurement, which one of those digits is estimated? This was last class. Which digit up there, which number up there has been estimated? The what? Oh, okay, so in this one, it's the 8. And in this one down here that I underlined, which is it? The 1. Why is it the 8 and the 1? What do both of those have in common? It's the last digit, right? Because we can estimate to 1 extra place value. That's where that 1 extra place value comes from. That's just a little detail that you're going to need to know. Okay? Mass, we've covered that. Okay? This is a pretty big slide. And so what I want you to write down is that in volume, we can get centimeters cubed. Hold on, don't write anything yet. If we do length, you guys have done this in math, right? Find the volume of that cube. Length times width times height. Your answer is something cubed, correct? So that 1 centimeter cubed is also equal to 1 milliliter. So this is one of the most beautiful things about the metric system and the ease of it. Notice how we're getting from a unit of centimeters. Meters is a unit of what? Length. And we're very easily getting into a unit of volume, right? In the U.S. system, we got inches into cups. That's not easily doable, right? There's conversions out there. I don't know what they are, though. Okay? But in the metric system, there it is. And then in the medical world, if you're watching medical shows or a doctor and they're pumping somebody full of a liquid or medicine, what unit do they use? 2 letters. Somebody said it. Not they don't say milliliters. Have you ever heard of cc before? They drain 5 cc's of liquid out of their knee. They pump them full of whatever, 5 cc's of Benadryl. I don't know, right? But that's the same thing as a milliliter. It stands for cubic centimeters. All right, so all of those are equal to each other. But yes, this is important because it gets us from a length into a volume or a volume into a length. Okay? So what we're going to attempt to do right now is convert things. We need to convert 749 milliliters to liters, and this is where we start our basic dimensional analysis. All right? And this right here is what I'm going to need to see for you to get your work points. Okay? And when I say, like, the sig figs and the scientific notation, those things get plugged into dimensional analysis, and we have made it a point to put a conversion dimensional analysis on every single one of your tests this year. Well, we did it last year, and so we're going to keep doing it this year. And so you want to talk about a skill that is used every single unit, it's going to be this. Okay? So what are the basics of converting, right? The first step is always, your first step is always to write down your given. So this is where math class really starts. I give you a word problem or even a basic conversion problem. You rewrite your given with the unit. Notice how I rewrote 749 milliliters with the unit. Your units are going to be so incredibly important. They get cumbersome. They get annoying because you're going to rewrite them over and over again. But they are important as anything else. Write it down. So in this case, we have a milliliter here. Right? And in math class, you learned that if you want to get rid of something, if something's on top and you want to get rid of it, what needs to go on the bottom? The exact same thing, right? If I have 2 times 2 divided by 2 times 4, what can I do to make that easier? Not subtract. What can I do to make that easier? Cross out a set of 2's. I have a 2 on top and 2 on bottom, right? Now it's just 2 divided by 4. You guys ever seen that before? Never seen that before? Well, that's what you do, okay? If it's on top and bottom, the same terms on top and bottom, you can cross it out. Well, why do I want to cross this out? Because I want to get out of milliliters and into liters. So your step 2 is unit on top and then unit on bottom. That's why we see this milliliter there. And then the last thing, you need to figure out your conversion factors. And that can be a difficult part, and we'll spend some time doing that. But those are the 3 basic parts of any type of dimensional analysis, any type of conversion. So now what I want you to get out is that table that I gave you. It's important. It looks like that. Okay? So what I want you to do, this is going to be kind of a notes. Thing. I want you to draw kind of a bracket from kilo down to milli. That's the section that you're going to have to memorize. Oh, you guys don't have that one. But you should have it on the front page. Yours doesn't look identical to this. But on the big side, from kilo down to milli, draw a bracket. And that's the section that you're going to need to memorize. Now, does anybody know the mnemonic device used for memorizing these parts of the metric system? King Henry something? Anybody? All right, so you ready? King Henry died by drinking chocolate milk. King Henry died by drinking chocolate milk. You're gonna want to have something like that in your head. Okay? So everything above this bracket and everything below that bracket, I will always give you. I'll give you those conversion factors. You just have to be able to use them. Okay? The ones within this bracket you need to memorize. So kilo, hecta, deca, your base unit. Remember all those base units? Everyone remember the base units? The big ones, gram, liter, meter. Deci, centi, milli. Why are the bottom three lowercase? Why is that? They're decimals. They're smaller. Your base is always going to be in your one spot. Your base unit will always be in your one spot. So if I have a gram, there it is, in your one spot. And the biggest reason why the metric system is so great is because it's base 10. We can just move the decimal if we wanted to. It's base 10. So that means deca would be 10, hecta would be 100, kilo would be what? 1,000. Deci would be 0.1. Centi is 0.01. Milli 0.001. Which is why you also see your powers of 10 here down the middle. All right. Now, what I want you to also look at is the things above and below that. Look at their powers of 10. After you get above kilo, what do your exponents jump by? By what? By threes. If you get below milli, what do they jump by? Threes, right? And you're going to need to use these, but you don't need to memorize them. Like you don't need to memorize pico or nano or tera or mega. But you will need to memorize the ones in between here and be able to use those, okay? So what do I mean by that? So let me get rid of this stuff over here. So what are you going to need to do and how to use these, right? So if I say I have 500 milliliters and you need to convert that into, let's say, liters. What I would need to see is all these steps of dimensional analysis, right? So look at your first step. What's the first thing we've got to do for dimensional analysis? Look at number 1. Write the given. Well, what's my given here? What's my beginning number? 500 milliliters with the unit. My next step, step 2 is what? What does step 2 say for you? Well, I've got the unit on top. Now what do I need to do? Put it on bottom, that same unit. Now, what goes on top? What unit am I trying to get to? So, let me get out of that. So I need to get into liters. So now step 3 is find out what your conversion factor is. So now we need to know what numbers are getting put next to these units, right? So where are we starting? Are we starting at liters or are we starting at milliliters? What's my given? So where are we starting? So if I say we're going to start here at milli, right? Milli is just a prefix. I could have milligrams. I could have milliliters. Anything. Millimeters. Okay? So I'm starting at milli. And then I need to jump to liters, which is my base unit. 1, 2, 3 jumps to get there. Would you all agree with that? Yes? Which means liters or milliliter, which one is my bigger unit? Liters, right? So because liters is my bigger unit, I'm going to put a 1 there. Well, because I jumped 3 times, that means on milliliter, I put 3 zeros. Which means, does that make sense? Because milliliter is smaller, should there be more milliliters in a liter or should there be more liters in a milliliter? Which one just makes more sense to you? More of the small and the larger one, right? Which is why we put the 1 on the larger and all the zeros with a smaller one, or the larger one and the smaller one. Okay? So what this is saying is 500 milliliters times 1 liter over 1,000 milliliters. So if I want to put this into a math equation, times 1 divided by 1,000. That's what you would put into your calculator. Everything on top divided by everything on bottom. So go ahead and do that in your calculator. Now, to do this mentally, anything times 1 is itself. You learned that in what, 4th grade? Yes? And then if you have 500 divided by 1,000, well, just knock off some of those zeros. 5 divided by 10 is, right? 1/2 is 0.5. Why would I count this answer wrong? How many sig figs do I start with in my given? How many do I have in my answer? Does that match up? Yes. There you go. There you go. All right. So this is what I would need to see for your work point. Let's see if I can. We've talked about that. Temperature scales. Prefixes are there. We talked about that. Okay. So what I want you to do is go to what you've picked up today.